thank you very much for the invitation. It's a great pleasure to be here and to be back in Israel. It seems like this is becoming an annual event for me to show up sometime during the late spring, and it's a pleasure to be here. So what I want to talk about today is non-volatile memory. I don't want to talk about the hardware aspects of non-volatile memory. I want to talk about how you program non-volatile memory. And this is joint work with a couple of people from my lab and a few other people who are not on this picture. Nashang was my postdoc for a couple of years, did the vast bulk of this work, and David is currently a graduate student who is hopefully hard at work on this as we speak. So let me give you a little bit of context to try to explain what the problems are in non-volatile memory. So there was persistent memory. This is where we got started. In fact, I think the first computer I ever programmed had core memory, magnetic core memory, and it was persistent. You turn off the power, and whatever was in the memory was there when you turned the power back on. We pretty quickly moved to DRAM, where that went away, and so you don't expect to turn off your machine these days and have it sort of have the contents of memory, but there's no reason why that couldn't happen. It's maybe the future, but that's not really what I'm going to talk about. But let me give you a little bit of context. So for a long time, there was this dichotomy. We had fast memory, DRAM, connected to the processor. You had random access to it, very low latency. And then you had non-volatile memory, which was your disk or your SSD. It was accessed in a totally different way. It was block storage. It was measured in milliseconds, typically with disks, tens, hundreds of microseconds with SSDs, basically a long way away from the processor. And it was accessed quite differently. There was typically a file system or something between you and the storage. Recently, we have seen the introduction of commercial products that are called non-volatile memory, which are accessed like DRAM or connected to the memory bus like DRAM, but are non-volatile. You turn off the power and it retains the contents of it, just like we did with SSDs and hard disks. So the characteristics that make non-volatile memory interesting are threefold. One of which, it's low power. And this is actually quite interesting if you're sort of talking about very large memories, terabytes. It only consumes power during memory accesses. DRAM, by contrast, has to be continually refreshed, so there's a continual power consumption by DRAM, and it starts to get to be very large in data centers and that type of characteristics. But that's not true of non-volatile memory. It's obviously non-volatile. You can turn off the power, and it'll retain the data. And unlike SSDs or disks, you can do direct access at byte level granularity, and the access time is measured in nanoseconds, not microseconds. So it has some interesting characteristics. Obviously, you can imagine lots of things to do with it. I'm not going to talk about all of them. I should point out that it is commercially available as of the spring. Intel has introduced a product called Optane DC, which you can buy, which is non-volatile memory that you can plug into your machine. So what's a use case for it? Let me just pick out one so we can talk about something concrete. So imagine you have a very large in-memory database in your service. It could be the World Wide Web. It could be the Facebook graph. It's stored across many machines in your data center. It's stored in the memory of the machines in the data center, and there's a lot of memory on each of these machines. So one of the reasons you might want to use non-volatile memory is, of course, the power consumption. But another one is the question of what happens when machines come up and down. How long does it take to reload their part of this very large database? And if you look at the access times for mass storage disks or SSDs and how long it takes to transfer into memory, it can take minutes to reinitialize a machine. So it might be better if this data was just stored in persistent memory so that the machine could come up and go down without losing the database. You would have to reinitialize things, yeah, but the data would stay there. So you could bring the systems back up very quickly and start responding to queries right away. So then Okay, so suppose we build a lot of these machines, stick them in our data center. The next question, the question that I'm interested in is, how do you program them? Well, let's start with how you don't program them. So you don't treat it like memory. So this is the classic example of transferring money between two accounts in a bank. You debit one and you credit the other one. If you do this with non-volatile memory, there's no real guarantee as to what results you're going to get. So the problem that occurs is that this is the model you're programming to. Like the processor is talking to the non-volatile memory directly. So when you do your debit, it goes to non-volatile memory, and then when you subsequently do the credit, it goes to non-volatile memory. This is the programming model. This is your model. This is unfortunately not the way we build processors these days. We have another level of memory. We have a cache in between the processor and the non-volatile memory. And so your writes actually go to cache. They don't go to non-volatile memory. The processor has a write back, the cache has a write back policy where it takes data that has been stored in the cache and eventually sends it to memory, in this case non-volatile memory. And it does it whenever it wants to. The policies are not really specified, as far as I know, for any caches that are commercially available. And so you can think of them as sort of random write-backs. So one of the things that could happen is you could write this one back before you wrote the debit back. They could occur in the wrong order. And so what's in non-volatile memory may be totally inconsistent with what you wrote in the program. So what do you have to do? Well, you have to flush the cache. So you have to insert Cacheline Flush instructions for each of the locations that you've modified, and then you've got to use a fence instruction, which basically makes sure that the flush instructions have completed. So it's a barrier here. This is kind of an ugly way to program, as you can see right here. It also has some fairly large performance implications that we don't like. The other problem, of course, is that it doesn't totally solve your problem. So, you can execute the first statement, flush it, do this, and then the program terminates somewhere in between the flush instruction and the debit instruction. And what do you get? Well, you've got one account that has money taken out of it, and it didn't go anywhere when you restart the machine. So that's not really what you want. So typically what you do is you make this atomic, you write it, put it in a transaction. You still have to worry about flushing it, or you have to worry about the atomic transaction, making sure that it flushes the data to memory. So the programming model has become a lot more complicated. You can't sort of think of it as a simple model, which is why I say caches are not your friends. But, okay, we'll accept that. Let's see what we can do about it. So one of the things that's interesting is that we need to also talk about sort of what the larger programming model is, not just the fine-grained programming model. So the model you should think of is that there is a persistent heap, which is part of your process's address space, but lives longer than your process's address space. So we start up a new operating system process. I apologize, it's dimmer here than it is on my screen. And it creates a memory space, transient memory in DRAM, and then it maps in the persistent heap. And so the persistent heap is now accessible to your process. When the process modifies data structures, this can stop. This all goes away, but the persistent heap remains. So this is the larger programming model that we're thinking of. And there's a life cycle, which is actually quite interesting for some of this work, where what happens is you start the program, it maps in the non-volatile memory, it modifies the non-volatile memory, it terminates somehow. It either terminates gracefully, the process just shuts down, which is good, or it could terminate with a power failure, or it could terminate with an error. Key thing we have to make sure is that the non-volatile memory is at a consistent state when the process terminates. Otherwise, when we restart the process down here in the recovery stage, we will not be able to recover it because the image that we see in the persistent memory will be very difficult for the program to use because it's not inconsistent. So there's this other step which we'll talk about as well. So this is where we're going. one thing that I'm going to use is the word consistent. And consistent in the case of non-volatile memory is, I'll define it sort of the way you would define it in terms of a database. So imagine that you had a program that was manipulating transient memory and non-volatile memory, and then all of a sudden it stopped for whatever reason. It stopped at some point. The program is consistent if you can restart the program, let's say at the beginning, not at the point at which it failed, but at the beginning, and you could continue executing from that point using the state of the non-volatile heap. And it would produce a result that could have been produced if the program had not terminated. So the result is legal in some sense. It's a legal output of the program, and it came about after this termination and restart. There are various things you can say about this. You can say generally error recovery of this sort is difficult if the non-volatile heap is left in an inconsistent state. The program moves between states, some of which are consistent, some of which are not. We would like to make sure that only the consistent states are captured in the non-volatile heap. And we'll talk about how to do that in this talk. So the way in which a lot of work has been published is basically says, wrap this in a transaction. The transaction worries about flushing things. So the programmer's abstraction is make sure that your manipulations of non-volatile memory are atomic in transactions. A lot of this is implemented using software transactional memory schemes. These are based typically on logging. There's undo logging, where you basically save the contents of a memory location in a log so that if the transaction fails, then you can restore it to the state it was before the transaction started. But there's also some work on redo logging, which saves the updated values so that they can be backed out as well. If you're interested, I can recommend a book. It has all the details you ever wanted to know about software transactional memory as of a few years ago. But I think all of you are probably familiar with transactions. So let's say that's the end of the background. Let's talk about some interesting ideas. So one of the things we started with is this question of, if you're going to build software transactional memory systems, how do you do logging efficiently with persistent memory, given that it has different characteristics than regular memory? Reminds you, a transactional log basically looks like this. There's a location, an address, and a value. So this could have been the value that was in the location before we did a write to it if you were doing undo logging. And then there's a pointer to the head of the log. So what happens here? You write a new location in there, you write the value in there, and then you extend the log to point to the next one. So this is fine. This is something that's done all the time in systems to do logging. How does it work with transactional memory? So this is our cache. This is the non-volatile memory here. And we'll be using this color code throughout the talk. Green is cache, blue is non-volatile memory. So imagine we have the state of the cache like this, and it's consistent with the non-volatile memory. And then we're adding a new element here. We write it into the free entry in the cache, in the log, and then we extend it. Now, we have this problem that we talked about earlier, that the cache writes back to the non-volatile memory in whatever order it wants. So one of the things that could happen is that we could change the pointer, and that could get flushed to non-volatile memory before we flush the contents of this log entry to non-volatile memory. So we basically have an inconsistency here. This log says that there's a valid entry here because the pointer is past it, but there's really no data in it. It would be whatever was there before because we haven't written into it. And so if the program terminated at this point, we'd have a great deal of difficulty recovering because we wouldn't have a valid log. So really what we want to have is a write back that occurs in the right order, but the way in which we do it is by doing a Cacheline Flush there. So the data gets written out at the same time as it's written to the cache, and then we extend it. We do another Cacheline Flush, and that gets written out there. So we have to do 2 Cacheline Flushes per log entry. The problem is that they cost a fair amount of time. Each one of those Cacheline flushes has to go to across the memory bus. It has to go to the memory controller. It has to go to the non-volatile memory, and then a response has to come back. And it's a blocking operation because we have to wait to see that the flush actually occurred. Latency, somewhere about 70 to 200 nanoseconds, depending on your system. And we have to do 2 of them. So we've taken something that's fairly inexpensive, if you're thinking about it in terms of cache writes, and turned it into something that's fairly expensive if you think about it in terms of elapsed time. The key idea behind most of this work is a sort of really nice observation that we don't actually have to do this. We don't have to worry about Cacheline flushes if we only have one cache line. And so here is the cache, here's the non-volatile memory, and these are just words in a cache line. And so what happens is that writes to the same cache line get written to non-volatile memory in the order in which they occur without any flushes. So if we basically have a Cacheline flush, what happens is that everything gets written to non-volatile memory. But if we just write to a word in the cache line, if it gets flushed, either because the cache does the flush or because we do an explicit flush, it goes and it gets written to the memory. And then if we do another write to the cache line, that also gets written to memory as well. And the order is preserved. It doesn't matter sort of what happens. We don't even need to do an explicit flush. If the cache flushes it to main memory, it will preserve the order of those 2 writes. And this is a key property, and one that we're going to take advantage of in a couple of different ways. The first way is we're going to basically do something which is to stick a valid bit in there. So basically assume for now that in the log entry we can find an unused bit and we can use it as a valid bit. So all of the data right now is consistent, it's all been written to memory, it's all valid. We just need to make sure that the valid bit is 0 before we do the write. We need to make sure that the valid bit image in a non-volatile memory is 0. That can be done in a variety of ways. The paper that I mentioned earlier on the slides has lots of details how to do this very efficiently. So when we start writing to memory, we can identify that this location has not been written because the valid bit is still 0. And we're taking advantage of the property, just go back, that we saw in the previous slide. We write the valid bit last in this cache line. We basically make sure the log entry fits in the cache line. We write the valid bit last. And so when we look in the non-volatile memory, if the valid bit is set, that means that everything else in that log entry has also been written to non-volatile memory. And we do it with a Cacheline flush, and we basically guarantee that all of this goes to non-volatile memory. So we've gotten rid of one of the Cacheline flushes there. We don't need to worry about the second Cacheline flush with this. We can basically write log entries by using half as many Cacheline flushes, which you might ask 2 questions, 2 reasonable questions. One is, where do we find room for a valid bit? And the answer is you can almost always find room for a valid bit. The paper has lots of clever different techniques. You can basically look in the addresses that are stored in log entries because various bits in the address space are not actually used on the x86. We can use those as valid bits. You know, the high order bits, typically the low order bits because you're doing word addressing, not byte addressing. We have some other techniques where you basically initialize the memory with random values, and with high probability you will guarantee that you will not see that value if you sort of write a valid log entry on top of it, and so you can distinguish between the writes and the non-writes there. There are also another technique we call flexible validity bits, where we basically keep track of the first bit that differs between the memory and the non-volatile memory and use that as the valid bit. Lots of details and examples in the paper. My contention is that you can almost always find a bit in a log entry for doing this. The other question is, does it matter? And so we implemented two write sets, basically a data structure that, what is this? This is the YSV. So it's basically a memcached-like system using a very write-heavy benchmark. There are two implementations. The red bar uses the single trip persistence set, which is the technique where we use a valid bit and only do one cache line flush. And then the blue bar is the one that does two flushes to the cache. This is throughput, so higher is better. And what you can see is with the size of the sets, there's a big difference with small sets, and then as the sets get bigger, it becomes less important, but we still maintain a performance difference. There's an advantage to doing only one cache line flush. And this slide is looking at the latency that is involved in going to memory. So again, what you see is with no added latency, we have a big performance improvement, but not doing a flush. And then the added latency, the performance goes down, but the gap is still maintained. Okay, so then the next question is, we got rid of one of the flushes, can we get rid of the other one as well? And this is some work that Cacheline is actually going to give a talk later today on, so I'm just going to sort of explain it briefly, and he'll provide a great deal more detail in his talk. So the idea here is that instead of doing logging, let's do checkpointing. Checkpointing is a technique that's used in a variety of different ways. It's fairly common in high-performance computing, where you sort of save the whole image of the computation so that you can restart it if something fails. It's kind of expensive, but it isn't done all that often. And so, what happens with checkpointing is that you make the process sort of yield control, stop mutating state. You make a copy of the non-volatile memory, and then you resume execution, and you modify this. And if it fails at some point, you have that copy over there, which is a consistent copy because the process yielded at a clean point, and you can restart at the point at which you took the checkpoint. Problems, of course, are that copying a very large non-volatile memory, well, requires as much non-volatile memory to copy it into, and it also requires a fair amount of time to make that copy. There's a long pause, and the way you typically deal with that is you don't do checkpointing very often, which means that the amount of time you roll back might be fairly large. If you do checkpointing once an hour, worst case, you could have to roll back, 59 minutes and 59 seconds if you fail right before the hour. So that's not so good. So what we came up with is another technique called fine-grained checkpointing. And we demonstrated it by taking a data structure, which is called mass tree, which was published a few years back now. It's a combination of a trie and a B tree, which is a very, very cache-efficient data structure. It's used in the silo in memory database, key value stores, a bunch of different applications of this sort. It's a very cache-efficient tree. And what we showed is that you can make mass tree persistent by using this technique of fine-grained checkpointing in cache line logs. And you basically go from 1 to almost 0 cache flushes in this case. And you introduce a relatively low overhead. I'll show you in this talk. The key idea with this is that we are going to break execution down into epochs, which are checkpoint epochs. We're using a 64 millisecond epoch because that's the time interval that mass tree uses for doing memory allocation and deallocation. We could use any amount of time. At the end of the epoch, we flush the entire cache to non-volatile memory. There's a new instruction, whatever it's called, however you pronounce it, instruction which flushes the entire cache to memory. Turns out it's a privileged instruction, so you have to do a syscall to do it. But even so, it takes 1.4 milliseconds on our machine, which if a 64 millisecond interval, it's 2.2% of the execution time. And then at that point, you know that the non-volatile memory is in a consistent state. You've got a checkpoint, basically, of the image in the non-volatile memory. And so if you have a failure during the epoch, we want to be able to roll back to that checkpoint after the last flush instruction and start execution. Problem is that, during the execution up to that failure, we have modified the non-volatile memory. And so we have to do a little bit of work to store the changed values so we can roll those back to the beginning of the epoch. And what we do is we use something called an in-cache line log, which is the trick that we talked about earlier of using writes to the same cache line to avoid doing cache flushes. So let me just sort of explain it using mass tree. So a mass tree leaf, a mass tree node in the tree, I don't know why it says leaf node, but it shouldn't, is 5 cache lines long. It contains a number of different fields. It contains, it contained 14 keys. We only use 13 because we take some of the space in it and use it for these logs within the data structure. So these are the fields that contain the values. And what we do is in each one of these cache lines, we take one of the values away and use it as a log for writes to the various value fields. And then we also have to log this field, which is called the permutation field, which keeps track of where the entries are in this node in the tree. And so when we write to either this field or some of these value fields, we have to store the old values in the cache line log before we do the writes. They're in the same cache line. We're very careful about where we place them so that the modifications get written to non-volatile memory in the same order in which we make them. So I'll just quickly go over this because Nashang in this talk is going to explain it in more detail. So take an easy case. We're going to insert, and there's some empty slot in the node. So we're going to insert into this empty slot here. This is the key, and this is the value. And the way in which this happens is that we basically just write into the key. We don't really worry about it because there was nothing in it before, so there's nothing to preserve. We don't need to log that. The value, similarly, had nothing in it before, and so we can write into that without worrying about saving the value before. The only thing that we have to save is this permutation field, which records that there was nothing in that field before. So what we do is we put it in here, and then we modify the permutation field. So if we have to roll back to get back to where we were before, we just take this value and we store it into the permutation field. These are going to get written in the right order to non-volatile memory. We don't really care about the writes over there because we don't need to worry about restoring empty entries. There are obviously cases where this will not work. If we don't have a non-empty entry, if we insert too many things into there. What we do in parallelizing mass tree is we just deal with these infrequent cases by logging the entire node in a conventional log. We don't use the in-cache line logs. We just log the entire node into non-volatile memory so that we can restore it. It doesn't happen all that often, particularly with short intervals, short epochs. The chances of doing 2 writes to a particular node are not very large. Similarly, you can do it with deletes. You basically have got to log the permutation there, and you don't have to worry about updates. I won't go into it. Nashang will do it in his talk. So how does it perform? Okay, so 3 bars here. The blue bar is conventional unmodified mass tree. The red bar is mass tree with some optimizations that we put in to improve its performance, basically using the same memory allocator that we use. It turns out there are a few things you can do to basically make it perform quite a bit better. And then yellow is with the in-cache line logging. And these are sort of standard benchmarks with various degrees of writing and reading and uniform and Zipfian distributions. I don't want to sort of go over all of the details. I just want to sort of point out that we are very close. I think the biggest difference is the write-heavy benchmark, as you would expect, where we're about 10 to 15% slower than mastery. And one of the other ways of looking at this, there's a lot more data in the paper, but one of the other ways that I sort of like is that this is basically looking at increasing the delay of going to non-volatile memory. Zero cost as compared to DRAM, and then a microsecond at the other end there. And what you can see is the blue is a uniform distribution and using logging. So you basically, instead of doing the in-cache line log, you basically log the changes. And you can see that there's first of all a large performance penalty, and the penalty gets larger as the cost of going to non-volatile memory gets larger. What you see with this one, the red bars, which are the in-cache line logging, is that there is a penalty as the memory goes up, but it's very gradual. You can barely see it in this slide. And the reason for that is that we don't do any flushes. We basically have the sort of major flush, and so we don't have to worry about the sort of latency of going to non-volatile memory. It basically is sort of all accumulated in the entire flush operation at the end of the epoch. So it's a much less sensitive to the cost of non-volatile memory. And it's also better than doing logging. So, okay, one more part of this. So one of the other things that we looked at is recovery, which is when something fails, how do you get back into a state where you can continue executing? And there are sort of three things, one of which is that the data that you have in your non-volatile memory may contain pointers to non-persistent data, and we'll talk about why that happens. Your memory may get mapped back into different places when you restart the program, and the code may be mapped into different places where you restart the program. And interestingly enough, all this could happen and is very likely to happen on a real system, but is never really sort of discussed in the research literature. So let's talk about what happens and how you deal with it. So suppose we have non-volatile memory, and somewhere in one of our data structures in non-volatile memory we contain a pointer to a network socket. Basically, you know, you're keeping track of where you're communicating with. That network socket is great. It works fine. You can access it from non-volatile memory as just as well as you can access it in DRAM, until, of course, you know, the power goes out, and then you restart. And you have a pointer to a non-operating socket. Not so useful. So your data structure in non-volatile memory may be consistent. We did all the things on the previous slide to show how to get things written to the cache lines, how to do atomic operations. But some of the data we wrote there is just no longer valid. So what do we do about that? And there's lots of possibilities for this. There's network socket, there's locks, there's process and thread IDs, file handles. The list goes on, basically sort of the transient state of a process that's perfectly fine while the process is executing, but goes away when the process goes away. And it's very common to store these objects in non-volatile memory. It makes it much faster to access them. They have to be reinitialized when you restart the memory. And so you have to traverse these objects in non-volatile memory. And if you think about traversing objects, it starts looking like garbage collection. Okay, so that's part of the problem. And I quote from a paper with a group from Oracle that looked at porting memcached to non-volatile memory. And what they said is basically initializing the non-persistent data is tricky. You know, the programmers sort of find it convenient to store it in the two together, and we don't find it very convenient to separate the two. So, you know, I'm a programming languages guy. This has got to have a programming language solution, and it will. Another problem, of course, is that I showed you earlier, non-volatile memory is mapped into your address space. So, you know, imagine we're running, we mapped it in, we said we want to map it at address 1000, and we have a pointer between these two data structures, and this pointer is in non-volatile memory and looks fine. Okay, power goes out again, comes back, we map it in again, but the kernel doesn't have to actually obey this. If you look at the semantics of it, what could happen is you could get mapped into not address 1000, but address 2000. And this pointer, which is in non-volatile memory, which previously pointed here, doesn't point here. It points back to where it used to go, and this object B is now at a different location. This is perfectly valid behavior. If you look at the mmap man page, it basically says if address is the first argument is not null, then the kernel takes it as a hint as to where to place it. So do you have to follow it? Nope. There are a lot of things that could happen. You could do an operating system upgrade between the two. You could sort of patch something. The non-volatile memory can grow and shrink, in which case it may not sort of fit into the place it was originally mapped. You could run under a debugger, which sort of changes your address space layout. You could do actions earlier in the recovery, which affect your address space layout, and it won't be possible to map back in, blah, blah, blah. The net result is you cannot depend on being able to map back into the same part of the address space that you were in before. Pretty much every non-volatile memory system that I'm aware of that's out there, at least in the research world, makes the assumption that this will never happen. And if it does, then they basically say, too bad, and you've lost your data. Because if you can't map it back in, you can't really do much with it. Third problem is that the data that you store in non-volatile memory can contain pointers to code. And, you could store objects, for instance, in non-volatile memory. Objects contain method tables. Method tables contain pointers to methods. Those methods may not be at the same place. There's something called address space layout randomization, which basically changes where all of the functions are in your address space to provide some more security. You could turn it off. Maybe it's not a good idea to turn it off, but you might want to do it if you're using non-volatile memory. So what do? Well, we're going to have to go fix up these C++ objects with method pointers. So what are the favorite solutions? Well, you basically say, you're not allowed to store pointers to DRAM in non-volatile memory. Forget it, absolutely. Problem goes away if you can't do that, right? Okay. There was a paper published. It doesn't really work very well, of course. Programmers want to use pointers to DRAM. The other alternatives, things that are sort of fairly ad hoc, self-relative pointers. So instead of storing a pointer into non-volatile memory, you store an offset from the beginning of non-volatile memory, and then you just do a calculation by adding the base of where the non-volatile memory is mapped in. Seems like a good solution. It's not supported by any programming language, so that you have to add a lot of code to your program to make that work, and somebody has to sort of read that code and understand that code. There are lots of ad hoc solutions. I think the typical solution is basically something like this. Put a comment in your code saying, yeah, there's a problem. Somebody should worry about it, but I'm not going to. Okay. What do we do? So what we did is we basically said, this is easy if you can change the compiler. So we're going to add some programming language support, and we're going to add some compiler support to sort of deal with all of these problems. And we're basically going to create a recovery procedure for each object. We're going to ensure that the object is well-formed after recovery, and we're going to make it transparent so that when your program restarts, all of this will have been handled. Your code will not have to know that any of these problems were problems that might have occurred. So we introduced 3 new keywords into C++. Transient basically identifies data that could be stored in non-volatile memory that points to DRAM. So here's a lock, for instance, and you basically mark that as transient so that we know that it will not be valid when the program is recovered. We introduce reconstructor functions, which are like constructor functions, except they're invoked at reconstruction time. And basically here you can reinitialize the lock if that's what you want to do. And then we introduced a new keyword for doing allocation in non-volatile memory, so we can identify when things were being identified in being allocated in non-volatile memory. These are basically the three extensions you need to C++, and you could add them to your favorite programming language. Key thing, though, is we're still using regular pointers. We're not using offsets. We're not doing anything that requires macros or sort of games with C++ pointer types. We guarantee that these objects will be zeroed when the program is restarted before the program accesses them. We have reconstructor functions that can do whatever initialization you want if zeroing is not the right behavior for a particular data structure. And we have an explicit way of allocating in non-volatile memory. And the workflow is very simple. We basically have a slightly modified version of LLVM that does this, that is extended there. It produces a runtime, which is used for reconstruction, and a database of the object metadata that we need to do the reconstruction, both of which have to be stored in the non-volatile memory itself so that it's around at reconstruction time. It's basically a lot of bookkeeping, but it's not very challenging bookkeeping. So after a failure for every live object, we zero the transient fields. We rebase the NVM pointers, so if you got mapped into a different part of the address space, we fix up all the pointers to non-volatile memory in your data structures. We fix the code pointers if the code is mapped in or randomized into a different location, and then we invoke the user-provided reconstruction functions. And we do this for each object. We don't do it all at once. It turns out that that could be quite expensive. Remember, we would like to sort of have fast recovery using non-volatile memory. So we do this in a lazy manner. We basically protect the whole non-volatile memory address space. And so when you first access a page in that address space, we go and fix up all of the objects on that page and then let the execution of the program continue. That means that at the beginning, there's a bunch of page faults when you access the data, and then gradually the page faults sort of become less and less frequent, and the overhead isn't there. So we did this for a couple of things. We applied it to Atlas, which is a system for running code using non-volatile memory. So what you can see here is basically the time, and this is the operations per second. This is the throughput of the application running on Atlas. And you can see that, for the first 100 milliseconds or so, the program is getting started, the reconstruction is getting started, and then the performance picks up pretty dramatically after we've sort of cleaned up the first few pages. And then you have these little spikes in the behavior as you are getting occasional page faults there. The performance is not very different from the code without the reconstruction occurring. We also sort of measured how much code you have to change in an existing application. So the Echo key value store is a sort of non-volatile key value store. We had to change 214 lines of code out of 22,000. So, around 1% of the code. It took, I think Nasrat probably a day or two when he wasn't familiar with the application to do that. One of the interesting things is, how do we know this works? So we did a really fun test. So what we did is we created a memory image using an application, sort of very demanding application that created objects. And we created it on our server using GCC 03, the original classes. We mem-mapped it at this address. And then we took it and we restarted it on Nasrat's laptop using code that was compiled GCC 00. We added a new field to every class as if we had sort of evolved the code. We mapped it to a different location, and the system was able to deal with all of these changes. The execution picked up right where it was, and it got the right answer. So sort of fairly robust under a lot of changes to the system. So let me just finish here and summarize. So NVM, persistent, directly accessible, randomly accessible memory, it's great. I think it's got lots of potential uses in the future, but you're going to have to be aware that it has NVM-ness, that there are caches that make it a little bit more challenging to program. There are ways to handle it, but this issue of having to write things consistently into non-volatile memory argues that you should think very carefully about using the idea of doing writes to the same cache line and trying to sort of serialize things that way. The key insight, caches lines are transferred entirely. How much can you pack into a cache line? Turns out you can pack an awful lot into a cache line there, more than you'd actually think. But don't forget that you're going to have to recover someday if things fail, and you got to get those details right as well. And the code for the modified version of LLVM is online if you want to use that. So that's it. I'm happy to answer any questions. Yes?
It seems like there's a lot of room for programmers to make mistakes. Maybe I could be wrong when they're doing their reconstruct function method. I'm wondering, have you considered approaches like managed programming languages, like as garbage collection is memory management? So basically, let the programming language and its implementation solve the problems for you, so that there aren't mistakes.
So there are other ways to do it, yeah. We didn't look at managed language. There happens to be a very nice paper that's going to be in PLDI this summer in a couple of weeks, talking about how to use Java, which is a managed language, and non-volatile memory. And they have a very different idea, which is they basically say you should only specify the root of the pointer into non-volatile memory, and everything else they sort of figure out using garbage collection and tracing. And, you know, it's complementary. It's something that's sort of quite practical to do in a language like Java, which maintains a lot of runtime information and has a garbage collector. It's less practical to see how to do it in a language like C++. So, you know, but going back to your first point, I don't think it's particularly error-prone what we suggest doing. You know, we chose very simple annotations intentionally so that you basically specify, you know, this is a pointer into volatile memory. Programmers in general know that. There are certain types of objects, you know, things like locks and so forth, which we can check fairly easily that you annotated them. There are things you could do wrong. You could take a pointer to persistent memory and put that annotation on it, in which case we would zero it out. That would be a bad thing for you, but you'd find that pretty fast. Yes?
I was wondering, like, if we were doing hardware changes, like have caches that has causal writes, we can think that the flash is in the order of writes. And also you could have a computer architecture where the memory has volatile memory and non-volatile memory. In the compiler, you declare the variables that the persistent parts go to at the end. Have you any idea of work is being done in this direction?
So I don't know any work that's being done. I certainly have thought about similar ideas. I mean, you can think about. The problem is that the caches work the way they do for performance, and how much performance are you willing to sort of trade off to have in-order caches? It's basically very similar to the argument why we don't have sequentially consistent memory on parallel machines. We could, you know, that's the way programmers think about writes to memory, but it would cost you a lot in terms of performance. I'm not quite sure what I would do with caches. Maybe if the cache was aware of sort of what the memory was, it could have different behavior if it was caching. But, you know, caches are sort of, you know, map in a lot of different locations in the address space during the execution of the program. So it's a little hard to see how that would work as well. Yes.
Sorry, but I think that at least Intel has introduced a number of new cache commands, flush off,
Yep.
WD, and so on and so on. Have you compared your results with an optimized version which is using these flush commands?
So we are using these cache commands. I think if you look at the ones that we didn't use all of them because we didn't have processors that had all of the the latest and greatest. But the general line of what Intel is doing, I think, is the sort of sensible thing, which is to basically introduce operations which give programmers control. But as you can see from this, it gives you control, it has costs, and it also sort of has semantics, right? It's not, in general, you think of a Cacheline Flush as being a performance optimization. In this case, because of non-volatile memory, it's actually a correctness issue. And so you have to get it right to make sure that things are persistent. So it's a little bit more challenging than that. I'm not sure that long run, that's really the best approach to solving the problem. Short term, sure, it makes perfect sense. Yes?
So if you have a non-volatile cache, do you think that will make things much easier?
Yes. Yeah, a very good question. For those of you who didn't hear it, suppose you had a non-volatile cache. The answer is yes. Then this problem would go away because in some sense the cache and the non-volatile memory would be part of the same sort of non-volatile structure. And we would be back to the simple programming model where you had a processor and you had non-volatile memory. But remember, it's a little more than just the cache. It also has to be the memory controller, which sort of contains in-flight writes to the memory as well, because that's a fairly long period of time over which you're going from the cache to the memory. So it's a little more complicated than that, but the basic idea I think is very sound. Yes.
So I think that some of these problems, at least, were kind of solved by the more classical persistent storage, right? Like block devices. For example, for block devices, we have battery-backed cache, right? For these types of problems. So what if we implement some of the concepts used today for block devices for NVM type persistent storage?
Yeah, I suppose we could have a battery someplace or a supercap someplace, but you want it on sort of every processor, and how are you going to power that part of the chip? I don't think any of these are unsolvable problems, but you have this trade-off. Do you really want to sort of change the processor and the cache, which is a very performance critical part of a processor, versus do you want to do a little more programming? I know what the hardware manufacturers will say. I know what the programmers are going to say, and they aren't the same.
The other proposal about the second part of the write elimination of doing a periodic write-back invalidate, right?
Yes.
And the write-back invalidate also implies that performance loss suffered because you invalidated the
Right. So there are new Intel cache flush instructions, which aren't the ones that we had, where you do the write back, but you don't invalidate, so it's still in the cache.
The entire cache.
Yeah, but also individual cache lines. There's a new cache line instruction. So yeah, you don't want to. In this case, you absolutely do not want to invalidate the cache line when you write it back to memory. You just want to sort of flush it out of the cache. Yes, back there.
You presented the changes to C++. Is there any effort to modulate this, something similar with the efforts that are already ongoing in optimization, for example, transactional memory, ATS, or any of the other?
So, I'm not aware of it. There may be something going on. As I said, a lot of the ideas in the software systems that support non-volatile memory came out of the transactional memory work, the software transactional memory work. But I'm not aware of any sort of further work to unify the two. So, what was another one? Yes.
How sensitive is this to the size of the cache line? Does the larger cache line help significantly?
This is like a PhD exam question. It's always a good one. Like, if you made something larger, what would it do? The answer is, from our point of view, yeah, if you had sort of a larger cache line, we could put more things in it, and we would have this property that sort of the rights to that larger collection of things would get saved. So, for instance, for the mass tree, instead of taking 5 cache lines, it might take 1 very big cache line. And then we would have a little more freedom in that case as to sort of where we store things and how we sort of do the in-cache line logging. We had to be very careful with what we did because we had to make sure everything landed in the same cache line. But I don't think it's first order, and I think probably the other sort of performance implications on the rest of your program of having larger cache lines might be more significant. So it might not be a good trade-off. That's a PhD question response. It's like, maybe. Other questions? Yes?
So I have one question, because you mentioned that you're writing back your cache in regular intervals.
Yes.
And you also mentioned that you don't know exactly how the write back strategy of the cache is working. So what is happening if some of the lines get evicted before this interval finishes?
Nothing. It actually makes the write back occur faster.
Okay.
So yeah, no, it's a good thing. It's actually a nice property of this interval-based one is that some of the data can get written back before the end of the epoch when you do the flush, and so it reduces the latency to do the flush. Were there other questions? Okay.